In question 6, we're asked to determine where the function is continuous. So to determine where the function is continuous, we break this up into two parts. Okay. What we're going to do is we're going to look at the boundary between each of these pieces, and then each of these pieces individually. So I'm going to do each of the pieces individually first. For x less than minus 1, 1 minus 2x is continuous by the direct substitution property. Okay. And so that's this piece, check. Now here for this middle piece, I can't look at the boundary points. I can't look at minus 1 and 1 using the direct substitution. I can look in between. Now for minus 1 less than x less than 1, x over x is undefined at x equals 0. Thus, f of x is not continuous at x equals 0. Okay. Everywhere else, f of x is continuous by the direct substitution property. Okay. Lovely. Now, for x greater than 1, root x is continuous by the direct substitution property as the domain of root x is 0 to infinity. Thus, we are continuous everywhere except 0 and possibly minus 1 and 1. So for each of these intervals, I went through and I just looked at the function within that interval. And within that interval, I checked to see, are there any domain restrictions? Is the function not continuous by domain restrictions? If it wasn't continuous by domain restrictions, that would give me a discontinuity. And I got one at 0. So we got to be careful that within these pieces, I don't have a domain constraint, or I don't have a discontinuity because of a division or a square root or a ln of some kind. Okay. We got to be really careful about our discontinuities within the functions. But then at the boundary of the functions, we still need to check. So we need to check at x equals minus 1. We need to check at x equaling 1. So at x equaling minus 1, the limit as x approaches 1 minus 1 from the negative of f of x equals the limit as x approaches minus 1 from the negative 1 minus 2x. which equals 1 minus 2 times minus 1, which equals 1 plus 2, which equals 3. And the limit as x approaches minus 1 from the negative of f of x, or from the positive, sorry, of f of x, equals the limit as x approaches minus 1 from the positive of x over x, which equals 1. As the limit as x approaches 1 from the minus 1 from the negative of f of x does not equals 3, which does not equal 1, which equals the limit as x approaches 1 from minus 1 from the negative of f of x, the limit as x approaches minus 1 f of x does not exist. Thus, the function is not continuous at x equals 1, or at x equals minus 1. Now we check x equals 1. Okay. So here, the limit as x approaches 1 from the negative of f of x equals the limit as x approaches 1 from the negative of x over x, which equals 1. The limit as x approaches 1 from the positive of f of x equals the limit as x approaches 1 from the positive of the root of x, which equals root 1, which equals 1. As the limit as x approaches 1 from the negative f of x equals the limit as x approaches 1 from the positive f of x equals 1, the limit as x approaches 1 of f of x equals 1. Now, f of 1 equals 1 over 1, which equals 1. As the limit as x approaches 1 of f of x equals f of 1 equals 1, the function is continuous at x equals 1. Okay. So we have that we are continuous at x equals 1. We're not continuous at x equals minus 1. We're not continuous at x equals 0. As we are not continuous at x equals minus 1 or 0, we are continuous for x in the interval minus infinity to minus 1, unioned with minus 1 to 0, union with 0 to infinity. And this gives us our where we are continuous. So now, for each discontinuity, we need to classify it as a jumper removable. So at x equals minus 1. So for x equals minus 1, we know that the limit as x approaches minus 1 from the negative of f of x exists, and the limit as x approaches minus 1 from the positive of f of x exists, but are not equal. Thus, we have a jump discontinuity. At x equals -1. Okay. At x equals 0, well, if the limit exists, then it's a removable discontinuity, because a jump discontinuity is where a directional limits exist, but the limit doesn't exist. A removable discontinuity, the limit exists, but the function is not continuous. So the limit as x approaches 0 of x over x equals the limit as x approaches 0 of 1, which equals 1. As the limit exists, we have a removable discontinuity at x equals 0. So we have a removable discontinuity at x equals 0, and we have a jump discontinuity at x equals -1.